Okay, Bismillahirrahmanirrahim. These are a few problems on chapter 16 for dynamics. In addition to the problems that we did in class, examples 1, 2, 3, and a few problems we did in class, let's do a few problems from the book, from the end of the chapter problems. See the suggested homework problems you have in Moodle. So pure kinematic problems where this disk is originally rotating with this initial angular velocity 8 radians per second, and it's subjected to a constant angular acceleration of 6 radians per second. So you want the magnitudes of the velocity and the normal and tangential components of the acceleration at this point, which is 2 feet away. It's an English problem, so it's a British customary unit system. We can translate it to like international systems simply by changing these into meters and approximately. So we want this acceleration and velocity at this point, which is about 0.6, around 0.6 meter, and 1 meter is about 3 feet and something and a third, and we want it at time of half a second. So the angular velocity at this time is given by the initial angular velocity plus the constant acceleration plus times the time. So this is given by the question as 8 and 6 radians per second squared, and this is 0.5 seconds. So this will be like 11 radians per second. The velocity, let's turn to the velocity. This is just the radius times the angular velocity at that point. This is nothing but radius 0.6, and the angular velocity is 11, just calculated. So this approximately will be like 6.6 meter per second. Of course, exactly, you have to do it in feet. And the components, the normal and tangential components of the velocities are given by r alpha, which is given radians per second. So this is 0.6. Let's agree on a 0.6 times 6. So this is about 3.6 radians per second square. And this is omega squared times a radius, which is 11 squared times 0.6. So it's about 72.6 meters per second square. These are approximate لأن الراديوس شوية مو مضبوط. A related problem, same given with the initial angular velocity and constant acceleration, but we want the magnitude of the velocity and the components of the acceleration at point B, which is around, let's say, 0.45 meters, 1.5 feet, as or after the wheel undergoes 2 revolutions. So from the kinematics point of view, we have to use a different equation. So this is omega naught squared plus 2 alpha c and theta minus theta initial. So this would be just 8 squared plus 2 times 6 times 2 pi minus 0. This would be around 14.66 radians per second. Again, for the velocity at point B, this is the radius at point B times the angular acceleration. So this is 14.66, just calculated. والradius قلنا, let's say this is 4.5 45 centimeters, and this would be 6.6 meters per second. The acceleration components, the acceleration at point B, the tangential acceleration is just alpha r, radius, so this is given 6, where radius is 0.45 meters. This is about 2.7 meters per second square, and the normal component of the acceleration at point B is just omega squared r, which is calculated 14.66 squared times 0.45, which is 96.7 meter square. Again, these are approximate because of the conversion feet to meters. And you notice a major difference between these problems, chapter 16, and the problems of chapter 12, for example, where we discuss just the kinematics of particles. Now there are rotations, there are other types of accelerations because the body has dimensions. And now we're able to ask about the velocity at different points within the body, in addition to the rotation. Let's look at another problem where the velocity and accelerations are not constant. So you have this gear, which is a motor, gives an angular acceleration that is a function of the angle theta. So 0.25 theta cubed plus 0.5 radian per second square. And theta طبعا is in radians. And this gear is initially turning at a constant at a given angular velocity, so 20 radians per second, and then this experiment, this movie, kicks in or is started. And you want to determine the angular velocity of gear B, the big one, after the small one, the motor, undergoes an angular displacement of 10 revolutions. So displacement, so to speak, a displacement, an angle displacement theta, مثل linear displacement x. This angle displacement is given. طبعا we have to do the kinematics in the angular frame of reference. We have an acceleration of gear A that is 0.25 theta cubed plus 0.5, and one of the three kinematics equation we have alpha d theta is omega d omega. When we integrate this, because this is a function of theta, so you integrate this from the initial theta to the final theta, and this from initial omega to final omega. So this is from 0 to 10 revolutions. So this is 10 revolution, everyone is 2 pi. So this is like 20 pi because of 10 revolutions, each one is 2 pi of this given 25 theta cubed plus 0.5. This is d theta of the gear A. And this is integrated from 20 to, as initially 20, and the final omega of gear A, of this omega A d omega. You do the integration, 0.0625 omega to the fourth plus 0.5 omega, so constant, and this is evaluated from 0 to 20 pi, and this is equal to 1/2 so omega A squared, evaluated from 20 to whatever we have, omega A at the end, the angular velocity after the 10 revolutions. So when you substitute everything, you get that the omega of gear A, the angular velocity is 1395.94 radians per second. And we know that at this point, they both share the same velocity. So this radius with this omega is equal to this radius with this omega because the velocity is the same, the linear velocity. So basically, omega A R A is equal to omega B R B. And just substitute this. So 1395.94, and the radius is 0.05 for A, and this is equal to omega B, which we want, and the radius is 0.15. And this will give us omega B at that point after 10 revolutions with this acceleration, 465 radians per second. A related problem right after it in the book uh, is this problem right اللي وراها على طول. So this is given a angular acceleration as a function of t and not the displacement. So this a is a function of t of time, and t is in seconds. If the gear is initially turning with a given constant angular acceleration, we want to determine the angular velocity of this gear when time is 2. So we'll integrate different kinematic equation, a different kinematic equation, which is basically the definition of this angular acceleration, d omega dt. So this is d omega is equal to alpha dt. We can integrate this and we'll get the integration from 20, the initial, to the final omega, which is, let's say, omega A, and this is just d omega A, and this is equal to the integral from 0 to t of this acceleration, which is 4t to the third dt. This will give us that omega A is t to the fourth plus 20 with this constant evaluated. Of course, all that remains is to determine the angular velocity of gear B when t is equal to 2. So at t equals to 2, you have the angular velocity of A equaling to 16. So this is 16 plus 20, so 36 radians per second. And at this point, they share the same velocity. So we could write again, so omega A of A and this R A at this point of this gear is equal to omega of gear B and the radius of that point of gear at gear B, and this is 36.05 is equal to omega B اللي ما ندري ايش كثر 0.15 اللي هو هذا. So this will give us omega of gear B as 12 radians per second. So same givens, different hidden information as the first problem. Another problem that is also uses the kinematics of rigid bodies. It's this problem number 16. We have a disk that starts with an initial angular velocity when this displacement is 0 and is given an angular acceleration that is a function of the position, the angle. So this is 0.3 theta radians per second square. and we want to determine the magnitude and normal components of the acceleration at point P, which is at a radius of 0.4, when theta is 1 revolution. We'll use the same equation as the previous problems. So this is omega d omega is equal to alpha d theta, and you can integrate this. This is integrated from 1 to omega d omega, and this is integrated from 0 to whatever theta we have, and this is given by 0.3 theta d theta. You do the integration and you will, this is 1/2 omega squared, evaluated from 1 to our omega, and this is 0.15 because you divide by 2, and theta squared, and this is evaluated from 0 to our theta. This will give you omega squared over 2 minus 0.5 is equal to 0.15 theta squared, which is omega is equal to square root of 0.3 squared plus 1.3 returned, and the half became 1. So at a given theta of 1 revolution, this is 2 pi in radians. You evaluate this expression and you get that omega is 3.584 radians per second. And then you use equations for the tangential and normal components of the acceleration. So the tangential is alpha r 0.32 pi, and this is equal times 1 revolution, and the r is 0.4. So this is equal to 0.754 meters per second square, and normal component of the acceleration, an n, not an h. This is just omega squared r. So this is 3.584 radians per second squared times 0.4, and this is 5.137 meter per second square, and the magnitude at point P is equal to square root of these two things. This is 0.7 whatever plus squared plus this 5 point whatever squared, and this would give you 519 meters per second square. Let's do one last problem for this rigid body motion involving a body that rotating, and we need the tangential acceleration and velocity of this body. So we have a motor with an angular acceleration as a function of time, and it's given an initial angular velocity of 6 radians per second, and we want the magnitude and velocity acceleration of block B after 2 seconds. The relevant kinematic equation, d omega is alpha to dt, and integrating these from 6, the initial one, to omega, final one, and time from 0 to 2 seconds. So basically this is omega minus 6 is equal to 2, this is 0.2 t to the third plus 0.75 t, and this is evaluated from 0 to 2 seconds. So this is the only unknown. So basically omega is, as after 2 seconds, is 9.10 radians per second. We want the velocity at this point, the omega, the angular acceleration, angular velocity times the radius. This is calculated 9.10 times the radius 0.15, and this is 1.37 meters per second. And the acceleration of body p, which is the acceleration of this point on the disk, is the tangential acceleration, which is alpha r, is given, this is 0.62 seconds squared plus 0.75 times 0.15, and this would be 0.472, so radians or meters per second squared. Let's do one last problem other than the examples we did here. Let's do like this problem, which is about a rod AB and a rod BC linked at B, where AB rotates uniformly, so constant angular velocity about the spin, and we'll call this omega, and we want to determine the velocity and acceleration of block C at the instant when theta, this theta, is 60. First, from the geometry, we can draw this. When this is 60, then we can say that we can use this L at this is like phi, and this is theta. We could write that this thing plus this thing is equal to L. So L cosine theta, and this one L cosine phi must be equal to L. So let's write this down. L cosine theta plus L cosine phi is equal to L. We also know that cosine 60 is 60 degrees is 0.5. So 0.5 and 0.5. So cosine 60 cosine theta plus cosine phi, which is 0.5 and 0.5. This is also equal to 1. You could get this results by dividing by L. L, L, and L. Now let's differentiate this cosine. You get minus sine theta, and derivative of theta with respect to time, plus or minus, this is cosine, so minus sine phi times the derivative with respect to time. This is 0, of course. You can multiply by minus 1 and get it a positive. So let's remove this. Part of this. So let's second time. So it will be like cosine theta, and then theta dot square, because we have another theta dot here. Let's put in parentheses, and then derivative of this guy. So plus sine theta, theta dot double dot, because derivative once here and once here. Plus same thing, so cosine phi, derivative will be theta dot, so we'll have theta dot squared plus sine phi, and then theta double dot. This is equal to 0. We know that when this is equal to 1/2, this is equal to 1/2, so when theta is equal to 60 degrees, we have phi must be equal to 60 degrees, so that they make up 1. So 1/2 or 1/2. So this equation tells us, let's say this is equation 1. So sine 60 is square root of 3 over 2, or sine of phi square root of 3 over 3. So theta dot and phi dot must be equal to 0. Theta dot is equal to minus phi dot, ولكن theta dot is the angular velocity, so e dot to any dot, this is equal to omega. Also we know that and phi double dot is equal to 0 لأنه constant angular velocity. So you can substitute all of these in this equation, let's call it equation 2, and you'll have cosine of 60. We know this is 0.5, and we know theta dot is equal to omega sine the square root over 2, and this is 0, and we have cosine is known, phi is minus omega, phi dot, and phi double dot, we don't know what this is, but sine phi we know. So you substitute everything in, and you will get that phi double dot is equal to, in terms of omega, theta dot. So this is all reduced to numbers. This is 1.155 omega squared. To get the speed of this block C, we'll define this datum, and we'll say that this thing, the position أول شيء, the position of block C, and we can see that the difference in distances, so the position is equal to L sine هالمرة مو cosine sine phi minus الطول الكبير minus الساين مال phi, so minus L sine theta عفوا. So this is one equation. You differentiate this and you'll get velocity of C راح تصير L cosine phi dot minus L cosine theta times theta dot. So let's put these in parentheses عشان ما نتخربط. You could also write the acceleration of block C. You do this product rule أكثر من مرة and chain rule. So this will be minus L sine phi times phi squared plus L cosine phi second derivative is vector term, so phi double dot minus L cosine theta double dot plus L sine theta with theta dot square. So at this instant, when theta is equal to 60 and phi is equal to 60 degrees, you evaluate كل هذيل and you'll get that the velocity of C is equal to L cosine 60 minus omega minus L, let's write it out, cosine 60 نص omega, this is equal to minus L omega. So this is minus لأن احنا سوينا minus, so this is this way. So basically L omega, this is L omega this way, so this is upward. And A of C, acceleration, is minus L sine 60 degrees times minus omega squared plus L cosine 60, etc., etc., etc. The only thing that we have from here, L this one is 0 و L so this third thing is 0 and this one في double dot اللي طلعناها minus thing. So you do all the substitution and you will get that this is equal to minus 0.577 omega L omega squared. So this is 0.577 omega L omega squared. This is minus, so this is going upward. So lots of geometric relations, and we want to relate basically the velocity هني with angular velocity and angular acceleration. This thing we solved actually in class, I think. Let's get the slides. Let's do this problem, which is about relative velocity. So you have h and phi or theta are known, and the speed of A and B are V unknown. We want to determine the angular velocity of the body and the direction of phi, the direction phi of VB. So basically عندنا ذيل magnitudes and the speed يعني, but we want the direction of this. So for the relative velocity, let's say, and this thing is like a hinge, and we have a omega this direction, and this thing is h, and this point is b with a velocity لما تكون هذه هني, this will be in this direction. So v of b with respect to a as shown كذي. And we could write this actually b as a vector of b is equal to v of a plus omega times cross product of the position of b with relative to a, and we can substitute these. So this is basically minus v اللي معطينا يعني cosine phi in the I direction. That's right, cosine phi in the I direction plus v sine phi in the j direction. So I or j direction, and this is equal to v cosine theta in the I direction plus v sine theta in the j direction. After resolving these into these two components, plus relative position, this is crossed with this, so basically this is minus minus omega in the k direction, and this is actually minus, so this is into the page, so this is clockwise, so this is into the page, crossed with minus h in the j direction today. Some forces to the right, they're positive in the I direction, 1, 2, and this one IUJ. So this is minus V cosine phi is equal to V cosine theta minus omega h. That's one equation. And also in the y direction, so this is positive this way, you have 1, 2 less. So this is sine V sine phi minus or plus V sine theta. Let's say this is my second equation, and from this equation we could see this phi is equal to theta, and that's from this equation. And also from this equation you'll have omega is equal to 2 of them, then we'll get the other way, and this is a minus, so get this one here, and this is 2v divided by h cosine theta. So that's your omega. Final sign minus, don't forget when you cross k with the j you'll get a minus I, so this minus they will result in just one minus. Let's look at another problem. Here you have a flywheel that is rotating with an angular velocity of 6 radians per second, and we want the angular velocity of this rod BC. So expect it to be this way, as this is going this way at the instant shown. So هذا تونا طالعينه, this is minus 1.8 in the I direction equals minus 0.5196 omega CD in the I direction plus 0.3 omega CD in the J direction, or product, cross product, so this is plus omega BC in the K direction crossed with minus 1.5 in the I direction اللي هو اتجاه هذا B relative to C. You could simplify, let's simplify this is 1.8, the I direction minus 0.5196 omega CD in the I direction plus 0.3 omega CD in the J direction minus 1.5 omega BC in the J direction. So هذيل مع بعض, and when you evaluate each component Li and J separately, you'll get 1.8 minus 1.8 is equal to هذه الآيات 5196 omega CD, and J صفر هني ماكو شيء is equal to الأخوان هذيل, so this is 0.3 omega CD minus 1.5 omega BC. So you solve these, they have two equations, two unknowns, and you'll get omega CD is 3.46 radians per second, and omega BC is equal to 0.693 radians per second. Okay, we can carry on and just look at these examples that we did in class, and let's do this. Let's do these. This is about the instantaneous center, zero velocity. So we have this disk rotating with a certain angular velocity, 4 radians per second, and we want to determine the velocities of points A or B or C. So basically you have this figure and you have this point A, and you have a triangle here at point C. The velocity is perpendicular to the line if you take this to be the instantaneous center. So first off, the velocity is at A is 0 because this is the instantaneous center of zero velocity. So that's done. ولكن هذه is right angle, and this one is 90 degrees, and this one is perpendicular to this. So we can write the position of point C relative to the instantaneous center of zero velocity as this one. This is 0.15, and this is 1.5, so this is square root of 0.15 squared plus 0.15 squared. So this is 0.2121 meters. And the relative position of B with respect to this instantaneous center of zero velocity is طبعا 0.3. This is 0.15 or 0.15, so this is 0.3 meters. The vector, the velocity of point B can be written in terms of the omega, the angular velocity of the disk, with the radius or the position of B with respect to this instantaneous center of zero velocity. So it is 4 times 0.3, which is 1.2 meters per second. On the other hand, this velocity of point C is the omega, and the relative position of point C with respect to this instantaneous center, and this is 4 times 0.2121, okay, and this is 0.849 meters per second. So you just make up these velocity and point E accordingly. The important thing to notice is that this is the instantaneous center of zero velocity. Let's do one more problem. We want to determine the velocity of this collar C. So we have the angular velocity of this link AB, and this is given as 4 radians per second, and we want to determine the velocity of this collar C and the angular velocity of this link CB, this one, at the instant shown. شنو الانستنت shown؟ and this one is 60 degrees. Theta is 60 degrees. So analyzing this geometry نشوف ان this is 60, this is 60, and this is perpendicular 90. So this guy is 45. So 180 مع هذيل. So this guy is 75. So we'll have this triangle that's 60, 75 degrees, 60, 75 degrees, and 45 degrees. And using the law of sines, we can say in هذه 45 is equal to this. So and over this over this, and this over this, and this over this, 75 over 350 كل واحدة اللي مقابلها. So 0.35 over sine 75 is equal to the relative position of the instantaneous center with respect to B over sine 45, and these ratios are equal to the relative the position of the instantaneous center relative to c over sine 60. This one 60 or 45. We could also compute from this هذيل هذا وهذا مرة وهذا مرة. So this is the instantaneous center with respect to B. This is given by this is calculated as 0.2562 meters, and R of IC respect to C. This is 0.3138 meters. So omega AB is nothing but the velocity B divided by R. I see instantaneous center of zero velocity with respect to B. So this is 2 and هذا half a meter, 0.5 meter, and this is VB. So divided by 0.2562. So this is 7.81 radians per second, and the velocity of point C is omega AB times this 3 point RICC. So this is 7.81 times 0.3138, and this comes out to be 2.45 meters per second. Let's do one more about relative accelerations. So we did velocities. We have a pulley A that rotates with a constant angular velocity and a constant angular acceleration at that instant at given values, and we want to determine the instantaneous angular acceleration of this pulley B. We can see that pulley A rotates about a fixed axis, so the velocity of point C is nothing but the angular acceleration of this pulley A times the distance R of point A, and this is 40 times 4, this is 0.05, which is 2 meters per second upward. So 50 millimeters is 0.05 meter times 40 radians per second. Let's draw the kinematic diagram for this pulley. So I have an inside track and an outside track, and this one has an angular velocity omega of pulley B, and there's a distance here plus the radius. So from here to this rope, this is 50, so 75, and this radius is 0.5, 0.25 for 50, that's 175. So the instantaneous is 175 millimeters, and the instantaneous center of zero velocity is this point C. Let's say this is C, and there's a velocity here just determined, which is 2 meters per second, and this is the relative position of C with respect to the instantaneous center, and this is the instantaneous center, of course. So we could write in omega point B اللي هني times instantaneous center of C with respect to instantaneous center is equal to the velocity at C فوق, and this will give me so V omega B is equal to EC divided by RC IC. So this is 2 divided by 0.175, and this will be 11.43 radians per second. You could also write for pulley A that the acceleration at point C, the tangential component is equal to the angular acceleration, which is given here, times the position of R A, which is 0.05. So this is 5 times 0.05. This will give 0.25 meters per second square. Also, we have to use the relative acceleration to point C and D, this guy, let's call it D. So I have inside and outside components. So this is the acceleration we just computed. So AC tangential, and you have this is 0.125, and مع هذا 5 so this is هذا من هني this is 0.175, and هذا 0.05, and also you have طبعا هني angular acceleration of B, and you have an angular velocity of B that we just calculated, 11 point whatever. So when you refer to this figure, you can write an acceleration of point D, اللي هي هني. So this is point D is equal to the vector is equal to the acceleration of point B plus the angular acceleration of point B crossed with relative position of D with respect to C minus the actual angular acceleration هذا, so B squared RD relative to C. So we can split these into tangential and normal. So you have AD tangential, in the I direction is equal to AC, the normal direction, and هذا I, plus 0.25 in the J direction, plus هذه minus alpha V, angular acceleration of wheel B. This is in the K direction, crossed with RC we just calculated is 0.175 I minus آخر شيء 11 this guy, so 11.43 squared times 0.175 I. So نقدر نجمعهم, بس let's write الnormal بعدين نسويهم مرة واحدة. So this is the normal component in the I direction. This is AC in the normal direction, minus 22.86 in the I direction, كلهم in the I direction actually, plus the أشياء in the J direction, so 0.25 minus 0.175 acceleration alpha b. This is in these all of them in the J direction. Hope I didn't mess this up. So evaluating I بروحهم والJ بروحهم, you'll see in 0 is equal to 0.25 minus 0.175 alpha b, and that alpha b is 1.43 radians per second square. So that's your angular acceleration of this pulley B. So what we did is we related it to this tangential component, and this is related to this tangential component. So by then we used the angular acceleration to write one acceleration in terms of another by using the relative motion. So that's the last part of this chapter 16.